Okay. So firstly, I want to highlight some of the contributors that helped make this competition possible. So I'm going to talk briefly about the motivation for this competition and the importance of safety in robotics. So as you know, today's robotic applications range from robot arms and aerial vehicles to mobile manipulation and self-driving, and these are powered by control theory. And they use handcrafted control laws for decision-making based on our prior knowledge. However, given the progress of machine learning and reinforcement learning in other fields like computer vision and natural language processing, machine learning promises approaches that allow us to go beyond handcrafted control laws, which are typically designed for a few tasks, and learn controllers even if we lack prior knowledge. And such an approach is necessary to make automation truly pervasive. However, there are a lot of challenges on the road towards deployable learning controllers, and these include sim-to-real transfer, computational efficiency, and most importantly, safety. And so in recent years, a wealth of research has explored how to extend safe and robust control frameworks with learning and how to scale RL beyond toy problems while encouraging safety. So let us look at a few different approaches very briefly. So classical control approaches fall into a category of model-driven approaches, and they typically consider a set of predefined robot dynamics and environments and design controllers for those conditions. And only a small portion of the world can be accurately modeled. And there is a clear boundary between what can be accurately modeled and what is safe and what cannot be accurately modeled. And so it is possible to give guarantees within specific contexts, but generalization, for example, to new operating conditions is very challenging. In the second set of approaches, or data-driven approaches, they learn a model of the world over time by collecting data. However, there is usually no clear boundary between what can be accurately modeled and what cannot be. And so this can allow for high generalizability, but providing guarantees is usually challenging. And finally, the combination of the two promises generalizability and guarantees. Using a model and learning together allows to improve the model of the world over time by collecting data through explorative actions with a predefined risk. So our goal has really been to move towards safe deployment of learning algorithms on real-world robotic systems. And our efforts can be grouped into three sub-goals. So the first is to provide an overarching review of progress made in safe learning-based control. The second is to develop a simple but meaningful benchmark scenarios to enable quantitative comparisons of safe learning-based control and reinforcement learning. And finally, to foster interdisciplinary research that can effectively leverage insights from both the control theory and machine learning communities. And this is through outreach events, workshops, and competitions like this one. So we've provided a few different work towards this. So the first is a review paper that sparked this, including open source code, the Safe Control Gem benchmark suite, which was used for this competition. And Adam will talk a little bit more about this. And finally, we have a safe robot learning webpage. And so please subscribe to our mailing list if you want to know more about this event and future events. So I'll now hand it over to Antonio to talk more about aerial robotics competitions and beyond.
Thank you so much. Antonio, currently at UC Berkeley, was also worked with Professor Scaramuza in Switzerland. He was one of the co-organizers of the Deutschland competition at the past weekends, I think. And their work essentially was one of the sources of inspiration for our competition, and he was very instrumental and helpful in organizing and defining the initial prospects of this competition. So please.
Thank you. Yeah, I guess you can see my screens. Otherwise, please tell me if there is any technical problem. Yeah, so my name is Antonio. I'm now a postdoc in Berkeley, in the Berkeley Artificial Intelligence Research Labs. I work with Jitendra Malik, basically at the intersection of computer vision and robotics. Yeah, I've had a little bit of experience with IROS robotic competition. I'm very happy to be involved in this one. And I'm now trying to explain why. Why do I like competitions? So I'll start basically with this statement that drone navigation is a research problem. And it has like many applications like search and rescue, delivery, exploration. And it is very important because most of the time we have perception-based control, right? The drone has to learn from its senses where to go and how to get there. And these systems are safety critical because, you know, if they make us mistake, things are gonna go bad. And drone navigation is, in particular in this application that I'm showing here, is one of the places where 98% usually is not enough, right? If 2 out of 100 times, like your drone falls down out of the sky, then it's gonna be a problem for the maybe products you're delivering, or could be a risk for like the people working around. So the thing is that like we are still in a very open research area where core components are still unclear. It is unclear what kind of representation we should use for like our navigation algorithms, for perception navigation algorithm, like explicit ones like maps, metric system, VIO, or more implicit ones like the one from that we, for example, get from a neural network. Also, it's unclear what kind of sensing does best fit a drone for which kind of task, like for example, RGB, depth, or like small lidars. And yeah, again, like what should we use? Like what should we prefer? A more generalizable learning-based approach or a more safety constrained model-based approach? Basically, like what we would like to understand is where to be on this line between end-to-end, that is usually pursued by big companies like DeepMind and OpenAI, and the classic perception planning approach, which is instead like the forefront of all successful robotic companies. So that's why to answer this important question, I think competitions are very important. And I think the reasons are clear. These are probably the thing that made the computer vision and the natural language processing community gave them so much progress in the last decade. The fact that people have standard metrics, so we can compare like according to the same numbers, sequestered test data, and public leaderboards. So when I write a paper, I don't have to go and run your code again. Like the numbers are gonna be there. And when we do this, like there are, of course, many important benefits, like you eliminate self-deception, like you think that something is good, but in the end, the numbers tell you it's not. You allow objective resolution between approaches, kind of, you know, like there are philosophies, people like this, people like that, but in the end, we only care what works, and basically speeds up progress. Of course, competition also have limitations, and most of them, I mean, the biggest limitation one is overfitting. That basically, and this happened for like this now the smallest data set in computer vision, like ImageNet, where the connection between the original problem of perception and the result on the supervised learning on the benchmark, now they diverge, right? Like presenting a number there is not meaningful anymore. So, but overall, I think the benefit outweigh like the limitation. And that's the reason why I really like this competition, like the Safe Robot Learning competition, because I think it really put emphasis on the 3 key points of drone research, which is simulation to reality transfer, which has really enabled a lot of advances in the last few years. robustness to uncertainties, like of any kind of nature, like for example, wind or like uncertainty in your mass and so on. And also like puts hard constraints on, for example, collision, some constraint violation, which again are very, very important when we start putting this system in practice in real world application. So yeah, this competition, I think it's really, really cool, really, really important. But let me tell you of a competition that we organized before that basically gave a little bit of direction for this one. We organized it like more or less 6 months ago at ICRA. We called it the Dodge Drone Competition. And in here, basically, participants were required to control a drone to avoid static and dynamic obstacles while flying at high speed. Right. So, yeah, this covers a different aspect of the competition that we're seeing today. Here it was more about how to, like fly fast, integrate vision, and basically all the uncertainty of perception. While here it's more, well, on another axis. Back in time at the Dodge Drone competition, we divided the problem in basically competition in 2 parts: state-based, where basically the approaches could access to everything, like the state of the drone, the state of the obstacles, and this allowed people to make progress extremely fast. And then the second one was vision-based, and I think this was kind of the most exciting one, in which basically the algorithms only had access to an RGB camera coming from the drone and the IMU, and yeah, they had to cope with that. So this basically introduced all problem of perception and was also more related to the final problem of control. And the goal was just, like we had no notion of safety, robustness whatsoever. We just minimize time while trying to avoid colliding into obstacles. And yeah, I mean, we had some like leaderboard and yeah, like people did great. I think I really like the solution of the vision-based system from like a team in Delft. And I think this is also a very important number. We also had like during the day, like some pilot controlling the drone and seeing how good they scored. Of course, they use vision. And it seems like the solution from people in Delft was not so far from like the best human pilot that we got in our pool at the day of the competition. So this was kind of an exciting result. People put effort in it. However, like something that I would like to notice is, oh, this should be a video. Let me see if I manage to play. No. Okay, so the video does not play, I'm sorry, like classical technical problems. So like basically like in the competition day, like now you'll see like there would be here like this small green dot in here is basically a drone. Some people brought their own drone, they start flying it around during the competition. And so basically it was like really, really a nice event. It was great for connecting with people working the same field. This is something that basically I did not expect. Competition is good for research, but also, for the networking aspect of it. And also something else that, I did not expect by the Dodge Drone competition is the fact that it had a much greater educational value than what I expected. Basically, I keep receiving email from like participants or that, for example, they want to use this as part of their CV for application in grad school, or people that want to do this like for writing papers and basically this kind of stuff. So I think this is maybe even more important than competition itself, like motivating students to get in touch with the problem. So yeah, I mean, like this, I think I mentioned a bit before, like the Dodge drone competition had some limitation, which we try to address with the competition today. The biggest one, of course, that we only worked in simulation. And of course, like we had no notion of robustness or safe, because like the drone was always constant, the same, and safety. Like if you would collide 1 out of 3 times, no problem, but you need to finish fast. So basically what you'll see is that we took this like famous saying, safety first, and we turned it around, right? We basically said, no, we don't care, safety last. And I think this is what like we have tried to correct a bit with the competition today. Also, I want to say that, like, I mean, we were aware of this limitation back in time, and this inspired some like of my recent work on, in particular, the theme of robustness. And in particular, what we were trying to study is like robustness to uncertainties for the problem of control. And uncertainties could be everything, like uncertainties in your hardware. Like, for example, what if you want a policy that can control any kind of quadrotor, like, for example, all quadrotors that I show in here, like from very small one of like 50 grams or so to very big ones of, you know, like several hundreds of grams. Usually controllers, they are specific, like, and they're very tuned to the platform they work on. So like, it would be very interesting if we could have like instead a policy which is universal, which is basically adaptive for whatever, it will work on whatever quadrotor it is. And this is also very important for application, because these uncertainty are problems when, for example, we crash, like some propeller damages, there is some wind, or like a payload is hunted. And we basically studied this problem. This was one of the first problems that we addressed when I arrived here in Berkeley. And we touched on it like using reinforcement learning. And we found out, like, I was actually very impressed by it, like extremely good results. We had to use like particular approaches for like basically allowing the policy to adapt to the quadrotor. But I was really impressed that, you know, a single policy could control basically all kind of quadrotors that we presented to it. And it was also robust to disturbances, mass, uncertainties, we pushing and pulling the quadrotor. So it was actually very good. Yeah, like we trained it, and here I'm gonna go very fast. Like we trained it with model-free reinforcement learning, PPO, in a 2-stage procedure. Basically, in the first stage, we trained the policy with information about the drone parameters, for example, its mass, like where it's center of mass, the strength of the motor, and so on. And then in a second phase of the policy, we estimate a latent representation of these parameters, so you can call it a form of latent system identification, by using an history of state and actions. So really as simple as that. What was my biggest surprise is that, like, in particular in the most difficult cases, like for example when we would push the drone, or like some of the motors would be fail and have like a loose efficiency, like our approach work much better than traditional adaptive controllers, like for example the L1 adaptive, both in terms of success rate and like in other metrics, like for example how well how well it keeps its height, and how good is tracking the commands of the high-level controller. Yeah, so that work was really inspired by that competition. And yeah, so like I think just now to quickly conclude, I think competition are extremely good. They foster progress, as they did it for me in this last work that I presented, but they're also very important for like education and networking. And then like this is like a bit of advertisement for like my latest work, is that which surprised me, is the fact that reinforcement learning policy, they can learn very robust approaches that are robust both to extrinsic factors, like for example wind, or extrinsic factor of the drone, like for example the changing hardware. Well, and with this I conclude. Happy to take questions, and yeah, thank you for your attention.
I guess yeah, next is would be Adam, who's PhD student here at the University of Toronto, is currently at IROS, and he's presenting Safe Control Gym, which is essentially the simulation software that was the basis for the simulation sim-to-real environment that you guys used for this competition. And the paper behind that work was accepted by IROS, so he's presenting later today, and is already I guess opportunity for him to rehearse once more, and for us to have an anticipated presentation of his work.
Awesome. Yeah, can you hear me and see my slides?
Yes.
Perfect. Yeah, I guess this presentation will be slightly different if you watch later at whatever 3 a.m. your guys' time, but yeah.
Oh, sure. I'll try to spot all the difference.
All right. But yeah, so I'll be talking about our Safe Control Gym software, which I think many of you are familiar with. And if you're not familiar with, you'll hear some of the motivation behind it and kind of how it works. Sorry, 1 second. There we go. Okay. So generally, when designing a controller for a robotics system, the engineer will use a prior model to control it, and ideally provide some level of safety and stability guarantee. And so kind of shown on the vertical axis here, we're kind of outlining different levels of safety guarantees. So an alternative approach, which Antonio kind of was talking about a bit, is controlling a robotic system using reinforcement learning, where the dynamics really don't have to be well known ahead of time in order to control the system. And now more recently, the reinforcement learning community has started to use to try and encourage safety and robustness of their controllers. And meanwhile, the controls community has started to combine their theoretical guarantees with machine learning in order to improve the performance of their controllers over time when the dynamics are not well known. And so this field of controlling partially known systems while providing safety guarantees, it's come to be known as kind of safe learning-based control. And ideally, the goal of this field is to develop control methods that rely on little to no prior knowledge while still being able to provide strong guarantees on safety. Now, there's a problem, however, as tracking progress in this field has been very hard across the two communities. For one of the reasons is the controls community likes to use tools kind of like MATLAB, C++, and often like closed source simulators. And often their code isn't really made public, or as frequently as much as the reinforcement learning community. And also the reinforcement community likes to use things like Python, PyBullet, OpenAI Gym, more open source, and different types of simulators. And kind of what we've seen is it's really hard to make comparisons when these algorithms are implemented in different code bases and different software suites. And this was a major motivation behind Safe Control Gym. So the idea is Safe Control Gym is an environment for both the reinforcement learning and control communities. And so in particular, our framework provides a symbolic prior model of the dynamics for each of our environments, as shown here, the cart pole, the 1D quad order, the 2D quad order, and the 3D quad order, which many of you used for the competition. And the idea is these symbolic prior models are really important for many control-based approaches. In fact, they're often required as like some sort of prior model. So additionally, we provide physical and dynamic disturbances, such as changing the mass properties of the system or injecting noise onto the inputs or observations. And so one example here we see is changing the pole length of a cart pole. And there's many other ones that you can implement through Safe Control Gym. Now, additionally, we also provide symbolic representations of safety constraints. So like state constraints and input constraints, which is not commonly found in any other gym environments. Yeah, and so our framework is freely available in GitHub, as many of you know, and we obviously encourage contributions, as many of you have started to do already. So in a little more detail, Safe Control Gym can be broken down into controllers that interact with environments. Environments are initialized with a visual model defined from a URDF file and in a PyBullet environment. And the user defines these things through a YAML file interface, which is like a common Python style, or just not just limited to Python, but many different types of languages as well. And they're able to also, through this YAML file, define a specific task which they wish to perform, such as stabilization or trajectory tracking. Now, a symbolic model is also generated alongside the PyBullet model, and this kind of acts as a prior model that the controllers can use. Now, also through this YAML file interface, you can also define constraints, these symbolic constraints. And as also, you can define external disturbances that can also be defined in this YAML interface. Now, when running experiments, one may initialize the environment into a random but repeatable initial state, and also a random and repeatable environment. And these are passed to the controller initially through initial observations and through like a Python dictionary. The controller then computes an action and returns that back to the environment, which is then stepped forward in time through the PyBullet simulator. And then it just continues to cycle until the task is deemed complete. So in addition to the gym environment itself, we've also implemented a number of classically oriented controllers shown here. And additionally, a number of reinforcement learning oriented controllers, kind of to give you an idea of how to implement your own, but also some common baselines for you to compare against when doing your research. Now, so ultimately, what we wanted to do is make simulations that are realistic enough to be used for real robotic systems, but also simple enough to use and also provide meaningful comparisons. And we wanted to make sure that it's appealing to both the controls and reinforcement communities. Now, with this in mind, here's a table that kind of compares how Safe Control Gym matches up against other commonly used gym environments. Now, in particular, we provide a broad set of uncertainty variations. We can apply many types of disturbances, and we're the only environment that provides symbolic models of our environments, along with symbolic representations of our safety constraints. So what can we do with Safe Control Gym beyond what you've already seen? Well, first, we present an example of how trajectories of many different types of learning-based controllers can be compared using the same environments on the same task. Second, we show how data training efficiency between different algorithms can be compared. So in particular, on the figure on the right, we see how Gaussian process model predictive control, shown in blue, achieves a far better data efficiency than PPO and SAC, reinforcement learning algorithms, but that it also starts at a much better performance due to the reliance on its prior model. Now, additionally, we can compare the robustness of different methods. On the left, we see how each controller performs when trained on an incorrect pole length. And on the right, we see how each controller performs when subject to varying levels of input noise. Now, we can also compare how well each method can satisfy different safety constraints. So one example here is trying to get a quad rotor to follow a trajectory that actually leaves a constraint region. So what you see here is on the far left, so what you're seeing here is the red line represents the trajectory we're trying to follow. And the black line is kind of the constraint boundary that we wish to stay within. On the far left, the linear MPC, which uses an incorrect prior model for its dynamics, leaves the boundary and has trouble tracking the reference due to its inaccurate model. In the middle, the Gaussian process MPC, which has learned to account for this incorrect prior model, tracks the reference well and also stays within the boundary perfectly. Additionally, on the far right, the safety layer method is also trained. Once it's trained, is able to roughly stay inside the boundary and track the reference reasonably well. So these are the kind of comparisons that you can be made with Safe Control Gym. And as you all know, we've started being able to connect to hardware. And as you participate in this competition, we've extended to actually implement the firmware from the Crazyflie in Safe Control Gym, such that you can do these kind of transfer learning tasks or transfer learning research, sim to real research, and also just see how your robust controller performs in the real world. I believe that this code is still currently only on the IROS competition branch of the repo, but it's going to be merged to the main branch, I think, in the coming months. And so what are some of the next steps? Like, where do we want some additional help? Well, first, more controllers mean more comparisons. So, I mean, in the future and currently, if you do end up using Safe Control Gym, obviously ping us and we'll try and incorporate whatever you've created into Safe Control Gym. We'd be happy to help. Second, we're looking for additional robotic platforms. So if there's anything that you feel really passionate about implementing, please reach out and we'd love to add it to Safe Control Gym. And additionally, we're looking to define more reusable safety metrics and reusable performance things, just to more formally define safe learning-based control. And thanks. And you can scan the QR code if you want to go to the website. I'm sure many of you are already familiar with the website, but yeah. I guess we'll do questions.
Thank you so much. Yeah, thank you so much, Adam. Awesome as always. And I guess you concluded, like, speaking about the extra development work that we did for the sim-to-real transfer, which is in fact the next section that Spencer, final year student here at U of T, will talk about. Essentially, was about interfacing the firmware of the real robot, the Bitcraze Crazyflie, with the simulation environment to have this type of zero-shot sim-to-real experiments.
Perfect. How's the audio? Can you hear me all right?
Okay for me. I think
Perfect.
it's okay.
Okay, so hi everyone. My name is Spencer Teetaert. I'm an undergraduate robotics student at U of T, and I've been working with the Dynamic Systems Lab over the last several months on the Crazyflies sim-to-real pipeline. So just to give you a little bit of background, the sim-to-real package is developed for the Crazyflie system. Crazyflie is a quadcopter released in 2011 by Bitcraze with the intent of being a research platform. Its source code is entirely open sourced, and the platform provides an onboard position and attitude controller, as well as providing APIs for sending off-board commands. Crazy Swarm is a package that was released in 2017 by James Price and Wolfgang Hollnig. It's designed to enable communication with multiple Crazyflies simultaneously, while also providing a handful of other useful features. These include collision avoidance and, more relevant to our competition, integration with motion capture systems. It also provides Python bindings for some parts of the Crazyflie firmware, most notably the trajectory generation, planner, and collision avoidance modules. Some additional related work to mention: they are in the process of developing Crazy Swarm 2. This includes ROS2 integration, but is currently missing many of the features of Crazy Swarm 1. As well, Kimberly McGuire, and I think she's on this call actually, created a Weebot simulator for Crazyflies, and this was really meant as a proof of concept earlier in this year as well. And this was developed kind of in, parallel with us, like we had overlap in development time. So Safe Control Gym, as Adam mentioned, is Dynamic Systems Lab's simulator for quadrotor dynamics. It's built on PyBullet and allows users to simulate quadrotors at specific control frequencies and higher simulation frequencies. This package gives users access to the motor controls directly and has been primarily used in simulation tasks so far. So what's missing from the system for sim-to-real? Safe Control Gym gives you direct access to motor forces and returns ground truth feedback from the simulator. It's great for simulation-only projects, but is missing a few steps when trying to implement solutions on real hardware, specifically for the Crazyflies. So to fly using a controller developed in Safe Control Gym, you cannot interface directly with the motors. Instead, there are several steps in the pipeline that affect both the timing of a command and the command's value. In the case of Crazyflies, this control looks a little bit like displayed here. So first, you would design a controller in simulation, and then to use the controller on real hardware, the controller sends a command to Crazy Swarm. Crazy Swarm sends the command over a radio to the Crazyflie drone. The Crazyflie firmware applies several different processing steps to your command that have potential to change its intended value. The output of the onboard firmware is applied directly to the motors, and in the closed loop case, a motion tracker system will send the new drone position back to your controller. Each of these steps has a runtime associated with it, and some of them change the actual command's value. This is where the sim-to-real package comes in. Sim-to-real is a module that is used directly in simulation. It wraps the Crazyflie firmware and provides a Crazy Swarm style API for users. The sim-to-real pipeline has two components. The first is a package called PyCF firmware. This is a Python wrapper for relevant CF firmware elements. It wraps firmware modules for handling both high and low level flight commands, as well as onboard controllers, which ultimately provide motor controls. Those that are familiar with the Crazyflie firmware might be asking, how does this differ from the provided Python bindings? First and foremost, PyCF firmware also wraps the high level commander, which allows for interfacing with high-level commands such as takeoff, go to, land, and the type. PyCF firmware is also built and tested for Windows, Mac OS, and Linux. And we did this really with the idea that it can be used by a wider variety of programmers without the normal build requirements for the CF firmware. The second part of the sim-to-real pipeline is our firmware wrapper module. This provides the interface between Safe Control Gym and PyCF firmware. This script is what provides the Crazy Swarm API for Safe Control Gym. Between the two elements, ICF firmware and firmware wrapper, we've enabled what we call copy-paste controllers between safe control GIM and real-world hardware. The goal with this whole pipeline is to allow zero-shot transfer between simulation and flying in real life. To enable this, our wrapper wraps any firmware component that changes the command value, runs at a specific rate, or that provides useful control APIs for the Crazyflie. Some modules that we have not yet included include all of the onboard communication protocols. We make the assumption that they run at a constant speed. Anything to do with sensor calibration, and that's because we can extract perfect information from the simulation, and so calibration is not required, as well as most drivers, most low-level modules, as well as the state estimation. The latter mostly due to time constraints, although with Vicon tracking and feedback on that front, this module becomes important. I know you're wondering, how well does Sim2Real actually perform? To test the pipeline, we designed 7 different trajectories entirely in simulation and ran the controllers zero-shot on real hardware for 30 runs each. We saw an average of 5-centimeter errors between simulation runs and real-world runs. Again, this is with zero-shot transfer, meaning no fine-tuning was done and the simulation controller was used as is in real life. In this video, you can see a side-by-side comparison of the simulation controller designed using Sim2Real and its real-world implementation. And as you can see, they're quite close visually. Like I said, this run had about 5 centimeters error throughout. So the hope with this is that you'll be able to design a controller using Safe Control GIM and be reasonably confident that it will be able to be implemented directly on hardware. Effective Sim2Real of a GIM-like environment is a very powerful enabler to research in control and model-free RL. So future work for this project includes working with Bitcraze to merge our PyCF firmware with their Python wrapper to the main CF firmware branch, doing more work developing controllers with and validating the Sim2Real pipeline, and the addition of more advanced state estimation time. So that's all I have, and thank you for indulging me.
So let's get this part. This part is possibly a bit redundant because everyone was here either organized or participated in a competition, but just for context. So the way we structured the program, I wanted Melissa to speak a bit about the general goals and overviews of our lab in terms of research for safe learning-based robot control. Antonio to speak about his experience and what he likes, I think is valuable about competitions. And Adam and Spencer, they presented some of the research and low-level implementation behind the tools that you have been using for this competition. This competition, as I said, probably everyone already knows, is something that we decided to organize more or less at the same time when the first version of the open source code for safe contributing was released. We thought it was an interesting opportunity to put the code out there and see and invite more people to provide controllers contributions and get in touch with us and have this nice interactive feedback in which we learn from the community, and maybe we can make our ideas and our perception of these problems a bit more widespread among researchers and industry developers. So the objective of the competition, more specifically, was to design a planner and a high-level controller for a Crazyflie quadrotor to safely slalom through a set of gates while also avoiding obstacles, and then reaching and hovering for 2 seconds, specifically at a predefined target position. The challenges that were in the realization of these tasks were uncertainties in the environment. This referred to position and the orientations of the gates, the obstacles, additional external forces to simulate low-intensity winds, uncertainties in the parameters of the aerodynamics, so mass and inertia tensors, provided through the simulation were not necessarily perfectly in sync with what would have been used by the physics engine to step the dynamics. And also we had we made the problem to include constraints around the boundaries of the flight arena to impose that the robot would not leave a certain flight space. And when we published the competition, we tried to design both the problem itself and the software interfaces in such a way that would have been appealing and amenable to approaches both from traditional controls, learning-based controls, and reinforcement learning communities. So for evaluation scenarios, we created 4 different levels with increasing difficulty in terms of safety and robustness that they would require by the part of the controller in order to be successfully completed. And we also added, as part of the competition, a 5th level for all of the solution that were able to complete all the simulation levels as the sim to real one. So I'm not necessarily gonna bother you with the detailed reading of what was the terminal output that everyone who's on this call has already seen. Essentially, if you also look back at the rulebook, the principles that we decided to follow in terms of scoring the solutions were to first score on performance, but performance intended as fast termination of the objective task, but with a strict enforcement of safety. So unlike what Antonio was saying before about dodge drone, the idea was not to minimize collision, but you could only complete the task if you would have 0 collision and 0 constraint violation, because we want to put this stronger, more type of safety that we wanted to see from the controller submitted to this competition. And then for controllers that will be able to achieve this type of safe performance, we would also secondarily score them by the amount of data efficiency. So essentially how much wall clock in real life and simulation clock in simulation would have been needed to collect the data necessary to train and optimize the controller that could fly that given trajectory. And in terms of statistics and submissions, we don't remember exactly when we made public competition, I guess mid-summer or early in the summer. We had expression of interest and registration from 36 teams, accounting for up to under 3 people. A few weeks ago, when the time came for submission, 9 teams and 36 people confirmed. In the following of the funnel, one of the 9 teams confirmed submission, 5 submissions were actually able to fly the course, actually able to fly, 4 were able to complete the course, and only 3 teams, in fact, were able to complete with perfect safety, which is still a great thing to see. So everyone who's on the podium today was able to succeed in the task of the competition with slightly different level of performance. And those are the points that we assign to the top 3 finishers. And I'm very excited to hear from them later on, like just after Kimberly presents the prizes for the competition, because I'm very curious to know how they did it, and I'm very curious to know what we can learn from them and which suggestions they have about the style of the competition, the structure of the competition, what could have been made more complicated, simpler, or more interesting or separate different avenues of development that they would have liked to see in the structure. And just tell me to go forward.
Yeah, of course. Just a couple of things that I would like to say. So, like Spencer already gave a great introduction to the Crazyflies. So, it won't be necessary for me to further really introduce the full platform. I think two extra things, at least for. Because there's indeed some development that happened in parallel regarding Crazyswarm 2 and the Python bindings. We actually have 2 controllers of the Crazyflie firmware that is now also in Python bindings. I don't know if anybody has tried it before already. And I'm also helping out Wolfgang Honig with the Crazyswarm to support. I actually presented that on ROSCON last week. And there is some more functionalities now available. So the president, so that if you check out the website there's some extra tutorials and some more explanation. So yeah, and I'm very interested in talking to you guys about integrating the simulation. We want to support multiple simulation backends, and really impressed with the safe learning gym. So I think it will be a very great asset to the project as well. So without further ado, so hi, I'm Kimberly from Bitcraze. So Bitcraze is a small company from Sweden. So Tobias, Marcus, and Arno, the three on the top, are the founders of Bitcraze. They started with Crazyflies 1, and that became so popular that they started a company about 11 years ago. So now we're with the Crazyflies 2.1 to be exact. And as you can see, you can the Crazyflies is the development platform. You can add all kinds of expansion dialects to add more sensing to the already standard IMU or more positioning systems, kind of pick and choose, let's say. You can go to the next slide. So the thing is that the firmware has already been explained quite a bit already. So I'm just going to focus on the hardware because that's going to be part of the prices. So Crazyflies, quadcopter, of course, brush motors. It's about 27 grams, 7 minutes of flight time with the stock battery. Although we're going to soon release a upgrade kit that will increase that. And also it's lift power as well. Like I said, modular design with expansion decks. And the firmware and software is all open source, and the hardware is open. So we provide schematics of that. I don't have one on me right now. They're all at the booth, but they're about this big. All right. Yes, exactly. Awesome. So that is, I think, with the motion capture deck, if I'm correct indeed. Yeah, awesome. Okay, if you can go to the next slide. So I will explain a little bit more about the decks itself. So we have a flow deck, for instance, for in the competition itself, there was the motion capture, but you can also do positioning, relative positioning with the optical flow and a range sensor. So the flow deck, or technically the flow deck version 2, has optical flow sensor and a range sensor, and then you're able to make it fly without any external positioning system. So you can fly it at home, which is really handy. You can go to the next slide. So something that I also presented during the ROSCON 2, the ROSCON presentation last week was the multi-ranger. I actually combined that with Crazystorm 2 to do a little bit of SLAM, let's say, of board, of course. Of course, I connected it with the SLAM toolbox, but it's technically like you have 5 of these time of flight 1D sensors that are pointing in 5 different directions. And you can either make a map out of it, or you can just do very reactive obstacle avoidance with it as well. I use them also during my own PhD research to do wall following, so they're all fun to work with as well. You can go to the next slide. So to add a little bit more autonomy to the Crazyflies, there's something called the AI deck. So it has a camera and some extra processing capabilities on there as well. So you can actually, you can either use it to Wi-Fi stream the camera footage and do some processing off board, but it's actually meant mostly for putting a deep neural network on the chip itself. So you can do full, onboard autonomy. So there is some really interesting work by Teetaert, or like the Pope platform people have ported a neural network on there that was able to follow corridors and roads and able to detect obstacles. So they are doing some really cool work with the AI deck as well. It's also based on one of their PCBs. Yeah, so that's kind of like, the very much the hardware. And the prices that I'm going to present for the one to first, second, and third place is a combination of those 3 decks and of course a Crazyflies. So if you can go to the next slide, I will present the prices. So the third prize is something called the STEM bundle, which is a Crazyflie, a flow deck, a crazy radio, and then you're already able to have a Crazyflie flying at home. The second prize is something called the STEM ranging bundle, and that has a flow deck, a multi-ranger, and a Crazyflie. So then you have a flying Crazyflie, autonomous Crazyflie that can avoid obstacles. And the first prize is the AI bundle, which is the flow deck, AI deck, and Crazyflie. And then then you have something that can not only potentially avoid obstacles, it can also detect or classify objects or see things, let's say. So a little bit more sensing and computational power on board of the Crazyflie. So yeah, those are the 3 prizes.
Awesome, thank you so much. And I know you also have to leave relatively early today, so thank you for taking the time to present the prizes to everyone here. And can I ask, what's the presentation you have to give today? Oh, you're going back to the booth? Or?
My presentation, I gave a presentation already at the ROSCON last week.
Yes.
So it was very ROS development based for Crazy, because we want to Crazyswarm 2 to be to actually make that the official ROS package for the Crazyflie, for either Swarm or just one. Makes sense. Still work to do. Yeah.
Yeah, and I know Wolfgang was on paternity leave.
Yeah, he's coming back soon. But I've been, if you look at the commits, I've been pushing a lot of commits. Yeah.
Nice. We'll be in touch with that. Then in terms of schedule, I guess we're 15 minutes at a time, but I would suggest we still take a 10 or 15 minutes break. And then there's the most exciting part of this meeting for me, where I get to hear from the speakers, from the participants, what they did in the competition. And actually, for the third place team, we have a recorded video. And for the second and first place team, there are speakers in the Zoom room right now.
Hello, everyone. My name is Zhang Kaizheng, and today I'm representing the ustc-arg team to share the technical solutions we used during the Safe Robot Learning competition. First, thank you very much to our friends in the Dynamic Systems Lab of UTIAS. Thank you for organizing and running this competition. And thank you for inviting us to share some of our immature ideas. Thank you. Now, I'd like to start with a brief introduction of our team. We are from the Information Science and Technology School of USTC, which stands for University of Science and Technology of China, a beautiful university campus located in Anhui Province, China. And here are some photographs of our laboratory. We have a lot of drones, and practicing manipulating racing drones has always been one of our group's hobbies. Our lab is under the supervision of Professor Wang Xin and Professor Ji Haibo. Well, okay. These are the members of our team, including 3 PhD students, Di Jian, Jin Tao, and Zhang Chenxu, and 4 master's students. As for me, I'm the least serious one here. Next comes the Eco-Solutions introduction section, which I will introduce in 5 points. As expected by the competition, we need to navigate the Crazyflie from the starting point through all the gates to the stabilizing position. So the real job to us is to plan a let's say, global collision-free trajectory. But before that, a global collision-free path needs to be established first. There are some proven algorithms, like, for example, the search-based A star or the sampling-based RRT star that can accomplish this. But what we used here is a simpler yet more practical method, which contains 3 main processes. The first step is initiating the path. And the second step is detecting collision. And the third one is correcting the path. During the first step, we initiate the path by simply connecting the starting position, the gate's positions, and the ending position, ignoring all other obstacles. Then proceed to the second step. We will examine every path segment to determine whether it's feasible or not. Well, how do we define feasibility? For example, whether the cross-gate angle exceeds a safe range, or whether the segment intersects with a cylindrical obstacle. Subsequently, for the cross-gate infeasibility, we will simply add a waypoint at the front of that gate. While for the collision infeasibility, we will search along a circle which is perpendicular to the intersecting line segment to find a collision-free point. In our case, I will take B2 as an instance, and then we will add B2 to the overall path. As for the construction of that circle, we will start from a relatively small radius. If all the points of that circle are infeasible, we will increase the radius by a small step. We will repeat this procedure until we find a viable point along that circle. Okay, now with a set of path points, we can generate a smooth trajectory via the well-known minimum step trajectory generation method. Let's recall the mathematical foundations of this method. First, we align the time steps according to the overall flight time and distances between every 2 adjacent path points. Next, we approximate each segment of trajectory as a polynomial of time. Additionally, we formulate the cost function as the integral or the sum under the discrete case of the square of snap along the trajectory. Then we formulate constraint equations based on the initial and final state restrictions, and also the continuity of the trajectory at every path point up to a certain order. Notice that the cost function will be in quadratic form, and the state restrictions and continuity constraints will be in linear form. Subsequently, we will get a typical convex optimization problem, which can be solved with various optimization tools, like the one we use here, the SignPy.optimization toolbox. Here are 2 pictures of our generated smooth trajectory. We can see that it looks smooth overall and can cross all the gates to reach the target position. But the waypoints of the gate's position appear to be off-center. It's because the real position of these gates will deviate from its nominal values. We will handle this problem in the following content. Well, there's another problem that should be noticed. The generated trajectory will deviate from the original path, as the right figure shows, which may lead to collision with obstacles. To solve this, we conducted an easy and straightforward approach, which is similar to our feasible path point search method. We first detect the two intersection points, and then we search around their midpoint for a feasible collision-free position with the smallest deviation from the original path. And then we add it to the overall path and regenerate the minimum snap trajectory. We will repeat this procedure until we finally get a global collision-free trajectory. With proper reference signals, we can move on to the control phase. Since the real mass of the quadrotor can contain a deviation of 25% or more, which will cause an definitely obvious steady state error in the height duration. Thus, we will use a long short-term memory network, LSTM in short, to estimate Crazyflies' real mass. The input of the network is a buffer with 5 historical data containing reference states, measured state, and the output is estimated mass deviation ratio. Together with the nominal quadrotor model, we can calculate a compensation term for the acceleration reference signal. In practice, we also implemented a low-pass filter to the compensation channel to reduce the noise caused by the inaccurate estimation made by our network. Now, this figure shows the training process of our LSTM. You can see the y-axis represents the relative bias ratio of the mass deviation. In the figure, the yellow line defines the training label, and the blue line represents the net's output. You can see our net can produce a convergence result very quickly, and thus it is able to provide a relatively accurate mass bias estimation. And this figure shows the height tracking performance of the Crazyflie, in which the red line represents the height state data when the Crazyflie's mass deviation exists, while its compensator does not work. In our case, the real mass is a little bit lighter than the nominal mass value. The blue line represents the reference height command, and the green line starts with no acceleration compensation before about 5 seconds, because our net is trying to estimate the real mass deviation during this period. And later, the compensator takes effect. It can be noticed that the tracking error can be significantly reduced afterward. To improve the trajectory tracking performance, we implemented a trajectory reference signal adjustment session, including a timestamp scaling module and a so-called reference position adjustment module. This module is used to reduce position tracking overshoot by slowing the quadrotor down when passing through gates. How do we do that? Assume the original trajectory is generated along timeline T, while the actual position reference signal will be sampled along a new timeline T star, which is different from the original timestamp. If we design the T star as a function of T, like this form, and design T star's derivative along T to be a multi-peak Gaussian function plus 1 for smoothness, we can remap the original position signal to a more slowly changing version. To be more specifically, a Gaussian function contains 3 parameters, and the performance of the Crazyflie passing through the gates can be adjusted by modifying these parameters. According to our solution, the mean value of the Gaussian function determines the position where the speed reduction process happens. And during our setting, it is defined as the timestamp at which the drone passing through the gate. The variance parameter can adjust the time range of the speed reduction process, and the peak of the Gaussian function can affect the degree of the speed reduction process. And then, as for the reference position adjustment, it mainly deals with the problem caused by the uncertainties of gates' positions. We record the distance from reference position to the gate's center when the Crazyflie detects the gate's real position for the first time, and use this simple proportional summation formula to calculate the actual commanded position signal that was sent to the Crazyflie, where d dot means the distance from the nominal reference position to the gate's nominal position, and delta means the position bias of the gate. Okay, and that's all about our technical overviews. So how does it really perform in practice? Let's check out the video recorded by our colleagues from UTIAS. Thank you very much, by the way. It is the planning phase. Now the drone has taken off. Now simulation has completed, and the real-world experiment has completed. Well, honestly speaking, I'm quite impressed that it can be achieved, in a few days to convert our simulation to real-world experiment, which really indicates that the powerful capabilities of this safe control gym benchmark suit. Brilliant work. Finally, the conclusion section. In terms of the structural design of the pipeline, we successfully constructed the pathfinding, trajectory generation, replanning, control compensation, and trajectory modification modules. We also designed all modules' Python interfaces and finely tuned their parameters on their different difficulty levels for real-time control. In terms of performance improvement, we adaptively proposed a global collision-free path construction method, a local feasible path point insertion method, a feed-forward compensating method, and a trajectory online modification method. So that's all the content of today's report. Some parts may not be clear due to the hasty preparation. If you have any related questions about our work, feel free to contact us. Thanks.
Very impressed. I'm a bit flattered, but also extremely impressed by the amount of work that this team has done. And also, I also want to thank everyone who's presented today, because as was mentioned at the end, essentially I gave our notification only a couple of days ago, so everyone was willing to present on such short notice. It's doing us an enormous favor. Thank you so much. And from an email I received, I think that the speaker of this video is not on the call, but some of his team members are going to be on the call today. Yeah, this is a simulation of Team Ekuflie. That's the simulation, and it seemed to be a result equally safe, but unfortunately a bit slower. And I think, I mean, I have a few ideas because I looked through the code, and I'm eager to know from the authors their consideration on that aspect as well. Thanks. I think Gerardo is the
yes,
can
that's
take it
correct. Can
Thanks.
you hear me?
I can hear you, and you should be able to share a screen.
Okay, give me a second.
Thank you.
Can you see a presentation there? Okay. First of all, thank you for the competition. It was really fun. We're team Ekuflie. We are all members of a company which is called Ekuflie. That's where our name comes from. We are a company that develops software for robotics application, usually around ROS, and we also have software development for other areas such as mobile and in some cases web, but very frequently also related to robotics. As part of the company, we have a small interest group that is called we call research and development, that we use to research topics that maybe we don't find every day in projects that we have and that we are interested in learning about, so that we take the chance to do development around those areas, do some research about that. And we have lately found that competitions are a very good vehicle for that, because they provide us with a very scope problem that we can research and try to solve. And so that's why we entered this competition, and as I said, it's been really fun to take part of. This is the team that was probably most involved in the competition, but there were some other members that were also collaborating with us and giving their opinions and giving ideas. So this is not totally the full team. There are other members. Some of them are present today here. We don't come from a control background, so when we started this competition, we needed to start by doing research from what were the usual approaches for this, and what kind of approaches will work better. So we started by doing by looking into what bibliography was around there, and after studying a number of papers and looking into a number of different approaches to this, we found that these papers from the robotics and perception group seem to match what we were trying to achieve and the approach that we wanted to take with this competition. So we studied them and we came up with an adapted version or with an adapted implementation of the work in these two papers. We need to say we have to say that these two papers are really clear in how they expose the algorithms and the approach and the control, and so we are very grateful for that. It was very easy to understand and to come up with a new adaptation of this. And also, we're also very grateful for the gym, because we also came up with implementations of MPC that were already available in there. So we could study them. We could study the models that were already the drone models that were available in the gym. That was all of that was really useful for us. So we're very grateful for that to everyone who created those materials. As I said, we started with these two papers. These two papers present a control method that is called MPCC. And the second paper, with the one time optimal online replanning for a child quadrilateral flight, is a complement paper that describes a method to generate a time optimal path that can be used with MPCC. We did not exactly implement that because we had performance constraints that we needed to conform to. So the biggest difference that we have regarding what is proposed in those papers is that we don't do online replanning of the path, which is one of the main proposals of those papers. Instead of that, we do all of the planning at the very start during the initialization phase of the software. We do the planning for the full path, and then we compile the Casadi controller that implements the MPCC controller only once at the very start of the initialization. And then we run whatever number of episodes we finally decide to run using both the precompiled controller and the same path for all gates. Since we only have partial information regarding gates, gate poses, we create a path for the approximate poses of the gates, and we need to correct that path later in real time, and we'll describe that later. The near time optimal trajectory planning that is described in one of the papers, in the one that is called time optimal online replanning, I will only describe it very shortly. The idea of that is that we need to generate a path that is smooth for MPCC to be able to follow it. It doesn't need to be a feasible path, physically feasible path for the drone, but it needs to be smooth. And the idea of the paper is that it generates a path by creating samples for different approach velocities and different directions for each of the gateways, and generating all of the possible combinations of paths between those samples for each of the gates to the next gate, and from there to the next gate, and weighting those edges that are generated by the time that it takes to get from one to the next. And then it applies shortest path algorithm to that in order to find the shortest path from the start to the end of the path. Since we are applying this to the full circuit, in our case, the optimization starts at the start pose of the drone and ends at the goal pose of the circuit. Another modification that we did to this algorithm is that we added collision checking here. We discard edges in the graph that end up in collisions with obstacles. So we do that before applying the shortest path algorithm, so that we come up with a path that a priori does not end up in collisions. So if we stick to that path, if we manage to stick to that path with the controller, then we will not hit any obstacles. Of course, we need to be conservative regarding the imprecisions in the pose of obstacles and gates regarding that. So we also need to use a worst case approach, when we discard paths. The MPCC trajectory controller that follows that path is a type of MPC controller that takes the path generated by the planner, by the previous planner, and tries to follow it as fast as it can, while at the same time reducing the error with respect to the path and minimizing the error to the path and trying to advance as fast as possible along the curve. For that, as I said, it is an MPC type of controller. It has a function that needs to be minimized on each iteration. Once that function is minimized, the control action that results from that optimization is usually applied to the system, and in this case, the drone. For MPCC, the three main costs that are associated to the function that is minimized are the contouring error, the lag error, and the progress cost. The contouring error is the tracking error, or the distance from the drone to the path that we want to follow. The lag error is the distance along the curve from the drone to a point that is moving along the curve that we want to minimize. We want the drone to keep up with that point that is moving along the curve. And the progress cost is the incentive for that point to move as fast as possible along the curve, and that's the one that the drone is chasing. There are a number of other costs also in the cost function there. Those are for smoothing the control actions mostly. In our case, we also have some others to improve the tracking when we were near obstacles and when we were getting through gates. The weights of the contouring and lag errors are a function of the position that we are along the curve, so that we emphasize or we incentivize the vehicle to stay close to the path when we are near gates, but we incentivize the vehicle to try to reduce the lag error instead when we are away from obstacles or gates, so that we can take shortcuts if possible in that case. We have a number of implementation considerations. The first one is something that I have already mentioned. Since this is implemented in Python, the algorithm that does the replanning, as is proposed in the paper, the optimal planning in the paper is too slow to be executed in real time in our case. That's why we decided to only do it once at the very start of the execution. Initially, we wanted to do it in real time. That proved to be not feasible. Even though we applied as many optimizations and scopes as we could, we reduced the number of samples generated, and doing the refocusing, we solved as many expressions as possible in closest form, and we simplified collision checking, and yet in that case we could not execute it fast enough, so we decided to execute it only once, and that had a cost for us, because since we cannot replan while we are moving from gate to gate, we cannot replan once we know the true pose of the gates. So we needed to come up with an alternative solution to this. The solution that we came up with is that we apply a small patch to the curve when we are close to the gate. We basically add a Gaussian function to the pose of the curve with a correction to the true pose of the gate when we are going through the gate. You can see that in the video here. You will see that the drone is following the reference trajectory, but when it's close to the gate, it actually moves to the right and goes through the center of the gate. That's because of the correction that we are applying to it. That correction has the shape of a Gaussian that is very small, with a very small deviation, with a very small standard deviation, so that it tends to go back to zero once we are away from the gate. And the other cost that not being able to replan had for us is that since we need to maneuver around this correction, and we only have about 40 centimeters once we know the true pose of the gate, we need to get close. When we get close to the gate, we need to be going slow enough so that we can actually do the maneuver without hitting the frame of the gate. So we needed to tune the incentive to move along the curve so that the velocity when getting close to the gate is not above a given threshold. We basically modulated the weight of the incentive to move along the curve so that if we are above a given velocity, the weight goes to zero, and the drone has no incentive to move through the gate at that velocity, so that the optimizer reduces the speed and gets us a slower speed. These are the results for the implementation that we finally submitted. We tested this by running about 100 times, about 100 different variations with different random seeds along the circuit, and we measured the execution time. We measured the execution times, and we measured the different types of errors that we could have. Our average time to get to the goal was about 10.7 seconds, with some deviation around that. We still had a number of a 2% rate of collisions with some of the gates. We also had some constraint violations. Those were 4%, but in that case, most of them were related to the initial state randomization. The drone was spawned too close to the limit of the workspace, and usually it would have a constraint violation when we're taking off. And we also had a number of issues with the MPCC optimizer not converging. So we had to deal with that by creating a fallback controller that would, if the MPCC optimizer will not return a solution, then we will just activate a second controller that will just try to follow the path at a very slow speed. Usually that was enough. Usually activating that controller for a single iteration was enough for the optimizer to generate a solution on the next iteration. So that it was not usually an issue that prevented us from going faster along the curve. And it usually only happened on very few places and with very few combinations of initial values. The highlights and the lowlights. The first one is that it worked since we started from basically researching from zero. So we are very glad that it worked and that it was performant. Another good thing that we noticed about this is that there are lots of parameters to tune. I also put this in the list of things that are not so good, because there are lots of parameters to tune, and it's very hard to find a combination that that is both performant and works in all cases, and that is robust to changes and to the different random variations that we had to deal with in this competition. No training phase is required for this kind of controller. We did not need to have a training phase, even though at some point we analyzed the possibility of learning the poses of the gates across different episodes, so that we could use a more performant controller in later episodes. And one thing that was really good from the gym was that the ability to be able to repeat the same scenario with the same seeds time after time, and with the same seeds allowed us to compare different tunings of the same controller and in a systematic way, so that we could run 100 different seeds and then repeat those same seeds with a different tuning and compare the results and come up with a good comparison regarding which one was behaving better and which one was more performant and had less collisions. On the VAT side, MPCC requires lots of computing resources. We were not able to run real time in most cases. Another thing is the real-time trajectory corrections. Just like I described, applying this Gaussian correction near the gates is very brittle and was very hard to tune for this, because if we go, as I said, if we got too fast to the gate, we will usually have a large rate of collisions to gates. And another thing that we noticed is that the point mass model for trajectory generation that is proposed in the paper that we use for path planning may not be a good model for the thrust to weight ratio that we had with this drone. So that's something that we think that we might look into in the future with more time. Possible lines of work, enabling online replanning by migrating the entire time optimal planning algorithm to a lower level implementation. This is trying to get more performance regarding the real-time functioning of the algorithm, replacing the Mellinger controller. One thing that we have is that since we needed to provide set points to the Mellinger controller, we needed to provide position, velocity, attitude, instead of the usual action control directly. So MPCC will provide optimization, and instead of just like in any other MPC algorithm taking the first control action, for instance 0, we needed to take the estimated position, velocity, and attitude for instance 1 and provide that as a set point to the Mellinger controller. That may also be an implementation issue with our implementation, but that's something that we found. We would like to see what happens if we, instead of that, have direct control of the propellers of the drone and apply the action control provided by MPCC. Testing adaptive control schemes to better cope with model disturbances. We did not implement that. We wanted at some point do that, but we did not. We ran out of time before that. And implementing longer prediction horizons. We use prediction horizon for MPCC of 10 iterations. We could not implement anything longer than that because for some reason it will not converge. Never. It will never converge. So that's something that we would like to test because probably that will behave better when the drone gets close to a turn around a gate and that kind of change in direction. And that's our presentation. And thank you again for the competition and for the materials, the team, and the resources.
Thank you so much. I mean, to say that I'm impressed is an understatement. Like, you'll see that gigantic amount of work in relatively little time. And also, thank you for noticing the aspect on the. Thanks for the honesty on admitting that you had certain collisions in your experiments. I didn't observe those. Essentially, I scored all of the solution using a random seed that I selected the day that I entered the lab and ran all of the experiments. And none of the teams that it's on the podium today had collisions in those experiments. Yeah, thank you for observing that. In terms of discussion and Q&As, I think some people from our lab will have a number of questions to ask you, but maybe we can do that at the end as a conversation for everyone.
Sure.
And then get screen share one last time. And Wanda, you can announce the winner once again. Okay.
All right. So this is the team H square, which got the first place of our competition. So in the real world experiments, it's actually pretty promising. And it like execute the trajectory without collision with the shortest time.
Okay, thanks for sharing. And then I'll leave it to Ashir, I think.
Yeah, sure. Let me just share my screen.
Thank you for taking the time. I don't know who's in which time zone at this point, but thank you everyone for being here.
All right. Are you able to see the slide?
Yes.
All right. All right. Hi, everyone. And yeah, before we start, I'd just like to say a big thanks to the organizers and Jacopo for like organizing this. We had a lot of fun and learned so much from this competition. Yeah. So who are we? Yeah, we have 3 team members. We are like a bunch of friends from Singapore. So we have New Sinyan. He's a research engineer and a master's student. And myself, Hashir. So I'm a robotic software engineer. And we have Wei Leong, who is also a robotic software engineer. So regarding our approach for this competition, we decided to use a traditional path and a trajectory planning approach. So we used the full state reference signal from the planned trajectory. And we also felt that reinforcement learning was not really required because we felt that the environment was very well defined in this case. However, we had some adaptations to the trajectory tracker so that we could handle some of the model inaccuracies and external disturbances that we'll talk about later. So looking at the high level architecture overview, so we will initially have an initial plan. So it will use the motion profile. We will put some spline waypoints through the gates. And then we have some initial obstacle avoidance based on the obstacles that are passed in a priori. And then in real time, we have a local replanning as well that happens when the correct gate position is known when you're very near the gate. So once this is done, we pass the reference position, your velocities and accelerations to the Crazyflie position controller. And then, yeah, so we also did like a small check for the gate orientation. So essentially we just needed to make sure that we were entering the gates in the most optimal way. So we just did a vector dot product between the gate heading and the displacement vector. Moving on, so we have the obstacle avoidance. So we tested out a few test cases of our own and found out that in practice, if we used our spline path intersected with the obstacle, we projected a new waypoint that was radially outwards from the original spline path, and we added that waypoint and replanned the entire spline again. However, we made an assumption here that the obstacles in these test cases are sufficiently sparse such that the new path does not intersect any existing obstacles, as it was kind of difficult to do this multiple times. So looking at some test scenarios, we can see here that even with the obstacles pretty near the gates or directly in the path, in general, the newly generated spline is relatively smooth and the drone is still able to travel at reasonably fast velocities. Okay, and now I'll pass on the time.
Hello. Yeah, so I'll go on to talk about the waypoint interpolation methods that we use. So initially, we decided to use p-chip, especially for the z-axis interpolator. So it's a piecewise cubic interpolation. Because the z-axis height of the gates have 2 discrete values, and the p-chip interpolator has no overshoot and oscillations. However, we noticed that the p-chip interpolator is C2 discontinuous. You can see in the blue circle on the right. You can see that the velocity profile of the z-axis is actually not very smooth. So instead, we decided to go with the quintic polynomial to stitch all the waypoints together on all 3 x, y, z axes. And this allows continuity in position, velocity, and acceleration of the drone. So as for the yaw direction of the drone, we decided to make sure that the yaw is always tangent to the trajectory, such that the drone is always facing forward in the direction of travel. This is because, like, typically for drones, there's a camera mounted and we wanted the drone to face the direction where it's going and to be able to see what's in front of it. We also had a constraint by setting the path to be perpendicular to the gate when it's going through the gate. So this actually, because the yaw direction is determined by the tangent of the trajectory, this constrains the first derivative in the quintic interpolation. So comparison between quintic interpolation and cubic splines, actually both are C2 continuous, but we decided to go with the quintic interpolation because we can define the second derivative at the waypoints, and the second derivative will map to the angular velocity of the drone as it's passing through the goals. So we set the yaw rate to be 0 at the goals. So this increase the turning radius of the curve and create a wider curve such that is better in the later parts when we come to trajectory tracking. Yeah, in terms of the time interval that was set between the waypoints when we use for interpolation, we actually just use the Euclidean distance between the waypoints to determine the time interval between the waypoints for the interpolation. So this is actually quite easy to do because it's there's no optimization required for this time interval. But one of the drawbacks is that this will actually introduce regions in the path where the kinematics limits might be exceeded in the motion profile. Actually, this drawback, we'll be talking about how we deal with this drawback later in the presentation. So as for the motion profile, we decided to use a linear segment with polynomial blend, or more commonly known as S-curve motion profile. We have kinematic limits of velocity, acceleration, and jerk. So these values for velocity, acceleration, and jerk are actually user-defined limits. They, of course, if we define them based on the model parameters, they will be the best, but you do not have to define them perfectly. There can be some amount of error there, and this will also be dealt with in the later parts. And also, the reason why we went with this kind of S-curve motion profile compared to a polynomial profile is because that the S-curve profile will actually spend a much longer time at a higher velocity, and thus is able to complete the trajectory at a much faster rate than a polynomial motion profile. So the mapping from the motion profile to the interpolated path is shown below. So actually, we have the S-curve motion profile on the left. You can see after we generate this, we actually map it onto the time interval for the interpolated waypoints. And then this then is mapped onto the full 3D trajectory of the drone. So this final trajectory is actually scaled by the total path length of the interpolated path to ensure that the kinematic limits are kind of being met. Yeah. Yeah, so next I'll hand over to Hui, who will talk about the rest.
Thanks, Xingren. So I'll start with the local replanning. So the local replanning was needed as the initial positions of the waypoints were not exact, and these exact locations were provided only when the drone was approaching the goal. So when the drone was approaching the goal, we'd add like a quintic polynomial segment from the current position to the exact waypoint. And to maintain that continuity, we would have to add the quintic polynomial segment as well from the new waypoint to the next waypoint location. We have a timescale factor, which I'll elaborate on later, which we will adjust accordingly to slow down the trajectory following if the actual waypoint location is too far from the initial planned waypoint location. Next slide, please. So now I'll talk about our adaptation algorithm for the trajectory tracking, which Xingren mentioned about. So as mentioned earlier, the downside of using the Euclidean distance between the waypoints to estimate the time needed on the path is that this could introduce regions in the trajectory where the motion profile exceeds the kinematic limits, such as at the curve sections. And so that led to our development of an adaptation algorithm for the tracking by introducing a time scaling factor. So the time scale factor is in the form of A log E plus B, where E refers to the magnitude of the position error, and A and B are hyperparameters to be tuned. So this adaptation algorithm slows the trajectory down, which helps to reduce the tracking position error. And the trajectory remains smooth as long as the tracking error remains smooth and continuous. So with this adaptation law, it helped to resolve the position errors due to the external disturbances, and also helped to reduce it from arising from the inaccuracies in the motion profile and the model parameters as well. Next slide, please. So the output of the motion profile and interpolators would give full state commands that are sent to the position controller on the drone. So this included the reference position, reference yaw, reference linear and angular velocity, and the reference linear acceleration. So the reference angular velocity in a way serves as a reference jerk for the controller, and in doing so, we made small angle assumptions on the roll and pitch axes of the drone. Next slide, please. So during the challenge, we found that our observations could be noisy at times. And if given more time to work on the challenge in future, we would implement Kalman filtering for the feedback of the sensor data. And that would also allow us to implement full state feedback, since differentiating the position estimates to give velocity 1 and differentiating twice for acceleration would result in a large amount of noise in our state estimates. So one assumption that we had to make in the obstacle avoidance algorithm was that the obstacles would be sparsely located. However, the next step for us in this would be to cluster the obstacles when there's a dense environment so that the drone can go around them. Another area of exploration would also be to use RL to complement our planning algorithm by learning the drone commands under environmental disturbances. Next slide, please. So here's a video of our drone in sim to real. Many thanks to UTIAS for the sim to real demonstration. Yeah, so we'd like to thank the organizers for organizing this competition and also inviting us to share our solution. Thank you, everyone.
Thanks so much. No, I repeat once again, I'm very impressed by the amount of work that you put into the solutions and also the amount of work you did in the last 2 days just to prepare this for us. That's extremely good. I mean, great to see, honestly, way beyond my expectation. That being said, if you want to ask questions, feel free. If you want to, if you have seen something in the presentation of the other teams that you want to ask them directly, I guess this is intended as an open conversation. Otherwise, Lucas can go with the scripted questions.
Yeah, so again, congrats to everyone. You did an amazing job. It was very cool to see all your results and approaches and how you thought about going about these different problems. Yeah, so we can just like get started with maybe talking a little bit about Safe Control Gym. So I guess like how was working with Safe Control Gym for you guys? How was your learning curve? What would have helped you like get you started a bit better? What did you like about Safe Control Gym in general? And what feedback do you have on it? How can we improve Safe Control Gym going forward? That would be helpful to know. Yeah.
If I can start, I think that some of the advantages I have already mentioned. I think that having the possibility to repeat the same scenario with the same seeds, that's a great thing, because as I said before, it allowed us to test repeatedly the same scenario time after time with different configurations, different controllers, and get things that we could compare from one to the other. I think that's something that was really useful, and that it's not very frequent. It's not always possible with some other simulation tools. That was great. The code was also very good. As I said, we used the MPC implementation that was available there in order to get started with Casadi. We had no previous experience with that, so we took that and based on that and the Casadi documentation, we managed to get our own implementation of a similar system. So as I said, we're very grateful for that. That code is really useful for someone who's getting started. I think it's great for learning beyond just simulation of this. One thing that we found at the very start when we began working with this and the API for the competition was not yet available was that we started by looking at the implementations of our LQR and ILQR and some others, and we found those to be a bit more complex than the one that was finally used for the competition. I think that the API for the competition was much more clear regarding what were the interfaces, the controller, what were the loops that were available. The implementations for the controllers that we had seen before had like lots of code for debugging and lots of code for data gathering that was kind of combined or mixed with the controller itself, and in some cases made it a bit difficult to understand. In particular for LQR and ILQR, that I think that was the case. I think that the MPC code was easier to follow. But the code for the competition, or the structure that was used for the competition, we found that a lot easier to follow and to understand and to actually implement on top of that.
Okay, thanks. Thanks. Adam will wrote the MPC parts. So we will take the compliment for that.
I guess this also ties into a question of what could have made the competition harder to maybe push people towards approaches that make fewer assumptions.
Like at one point, I decided, like, one of the choices we made was to make it somewhat sufficiently simple, which is something that the team from Singapore ended up mentioning. They did make assumption on the sparsity of the obstacles. The map was still randomized, but somewhat repeatable. I imagine that many of the solution here would struggle a bit more if the map reset itself.
Indeed, I think that the fact that the gates were mostly in the same places at all points, I think that tended to cause the solutions to probably overfit to the circuit a bit. Because even though we tested a large number of samples with random variations of the scenario within the boundaries of the distributions used
the distribution relatively matters, yeah.
But they were limited. So even though despite that, there will not be large changes in the scenario. So probably if we change with that different setup of the gates, probably we're going to find more issues than we did with a large number of repetitions of small variations of that scenario.
But there is a question in the chat as well, Lucas. Maybe you want to read that?
Yeah, so there is a question for the Ekuflie team. The question is, how is MPCC deployed? Do you generate motor commands directly? Are you not using the Crazyflies native controller?
No, we are using just the same API that the competition provided. Instead of, usually the MPC controller will generate the control actions directly, which in the case of the drone will be the propeller thrusts. But we did not have the API to provide those to the controller. We could only provide the set point for the melee share controller. So what we did was instead of recovering the thrusts from the solution provided by the optimizer, what we recovered were the next or the position velocity and attitude for the first iteration for the iteration 1 instead of the control actions for iteration 0. So that was our solution that worked. It's not very typical of MPC systems. That's why we would like to test how it behaves if we actually could provide the control action to the thrust.
Mm-hmm.
Yeah, what rate were you able to get your MPCC work running at?
Running on an i7, we managed to get. It depends if we had the graphical interface active or not. If we disable the graphical interface, it got to a real-time factor of 1.3. So it could actually run at the 30 hertz of the control loop. But if we had the graphical interface on, we could only get about 0.66, 0.7 or something like that. It depended on the optimizer, but it usually only took about 20 iterations to converge. In that case, we will get to 0.6, 0.7 with the graphical interface 1.3. In some cases, it will run for longer. It will take a larger number of iterations, and it will eventually either converge, or in some cases, it will not converge at all. And those were the cases that we needed the fallback controller for.
Yeah. Were you using like which solver? Were you using IPOpt?
IPOpt.
Yeah.
Sorry. Okay.
Adam, we have the code on here in the lab if you want to come and run it.
Yeah. I might take a peek.
Like one thing that we were seeing in experiments, their solution would run a bit slower in real life is because some of the codes to solve or to IPOpt would be slower than 20 milliseconds, 25 milliseconds, which is what would be needed to stay within the 30 Earths in real life. And Gerardo also gave me a few suggestions how to run further experiments in that direction. I'll try next week because I was time limited with this. But thank you so much for all the insight on this.
Yeah, do we have anyone from the other teams who wants to comment on any of the points that were mentioned? For example, yeah, like the working with safe control gym, also about like what could have or what could make this challenge even more challenging. I mean, this is also hinting at what might come.
I also want to make it easier to understand. Like I would like.
What is it?
I'm impressed by the amount of work that the people who are here today did. Would have possibly, I think, would have been nicer to have more participation in the final stages of the submission if even smaller teams had been able to get submission. I'm super glad that the people who won it. It's a relatively small team of 3 people. Several of the people were trying to develop a solution by themselves and contact me over time. They weren't able to make a submission in the end. So if there are certain corners that you think should be cut, for example, everyone uses CMD command full state as an interface, right? Did anyone use takeoff or lands or go to? No. Okay. Just expansive is also free.
Going to say the other API element that we didn't include was I know Crazyflie has the ability to upload full trajectories, so that could be something that we look at including in the future as well. Rather than forcing teams to send commands at 30 Hertz, you could send maybe 1 command every gate. I don't know, might be something to look at in the future.
One thing would be very interesting is to be able to do something a bit closer to motor input command. The problem is we are limited in frequency from what we can send from the ground station. So everything that's interactive and feedback loop would be on board, and the microcontroller obviously has limitations. Actually, the team that won and is receiving the AI deck, maybe there is more compute power on that one. I don't have one of those. Maybe you can try to do more advanced things than we currently have. We should get a few AI decks.
Hello. Yeah, I'd just like to say thanks for having a competition. I just have some like, I'm not sure like is it improvement or what, but like because at first when we took part in the competition, we thought it was more of a controls competition, and yeah, but we found out later there was more of like trajectory planning because like we can only send full state commands. So like, is this a limitation of the drone itself, or is it a simulator? Because like if you want to implement NPCs, we would typically want to have access to the motor controls and also to be able to receive like full state feedback if possible. Like, does the drone only provide additional sensor readings?
From my perspective, yeah, it's the limitation is the amount of compute power that's on board, because if you want to do directly motor control, we should implement in the firmware, which is written in C. That's fit on a STM32 microcontroller. What we were doing, and those type of solutions with direct motor input with complicated optimization on top of it can be run in simulation in safe control regime. That's mostly what Adam's work is based on. For the competition, we had to make a choice that we really wanted to have real life experiments. And so we had to fit what was possible to run in simulation to the compute limitations of the real system. And so that's why we looked at Crazy Swarm, which is a very nice project by USC, University of Southern California, and now TU Berlin. And we use their ROS communication packages and interfaces to have somewhat of a flexible API off-board that can be accessed in Python, which is essentially what you've been playing with. But then the the feedback low-level control is Mallinger controller, the PID controller that's already in the firmware. At some point during the design of the competition, Melissa Sik is not here, Melissa's here. We were thinking of should we let the participant be able to play with the firmware as well, like allow you the possibility to change some of the functionalities of the low-level controller. But we deemed that to be a bit too complicated because it would have required either you to write also C code or for us to convert whatever logic you were coming up with to C, which is, and also C with memory constraints, which is not obviously always straightforward, and refresh the firmware in between runs. Because it would be nice, to be honest. I wish we had a Crazyflie with a bit more compute power to do these kind of things. But right now,
correct me if I'm wrong, but there is a way to send thrust commands, but usually it's just the latency is too much that, and like you can't get enough high enough rate that it doesn't.
We can use the
work.
same communication protocol to send whatever we like. It just and the advantage is because we're using Vicon, we don't necessarily need the state estimation that's on board. We have a fast 200 plus hertz estimate of the pose of the drone, but the crazy radio would likely see a bit too slow. Honestly, I think Federico and you could try a bit more in that direction because
I mean that's the plan.
Yeah, I don't think aggressive flight is possible in that, but something a bit more, something could still be possible, I think.
Yeah, so we're currently looking into sending like roll pitch yaw commands to the Crazyflie to have like maybe some more lower level controls for the Crazyflie. If Federico is here, I am not sure if you want to comment on any of how this is going in front of everyone, but yeah.
Yeah, I'll keep you updated. I'm curious if it's going to work as well as we need it to work, but I think there should be a way to make it at least function like fairly well.
Yeah, and so this could be an option for having more control, more fun with like actual controllers, and then we could also like think if we want to have maybe like tracks for control people, tracks for planning people. I think there would be like different options of having also like easier challenges, harder challenges. There's like definitely certain ways how we can do this competition going forward. But yeah, that's a good feedback about the framing of the competition. Yeah, thanks for that.
A question in the chat about wind. Yes, disturbance is random. I chose not to like. Although, if you want to have a monodirectional wind field in the simulations, relatively straightforward to implement just by changing the YAML configuration file. I was thinking that I would have not had a good way to reproduce it in real life because.
I mean, we have fans, right? We could put a fan.
You want to come back to Toronto? We have to play with the fan. Yeah, no, sure. I was.
I could stand there.
Yes, but yeah, it's honestly, yes, probably for the next iteration, maybe something a bit more interesting in terms of wind and aerodynamics disturbances could be made, because that would definitely make the Teetaert jump a bit more complicated because that physics is a bit harder to model. And I was answering your question, which is in the chat by Jim.
Yeah, the question was, is there currently no wind disturbance added during the real race?
One thing that we noticed is that the scoring seemed to help a lot the solutions that require only a single episode. It's like the penalization for having even a second episode to learn the poses of the gates, for instance, was not worth it from a scoring perspective. Initially, we wanted to go with an approach that will learn whether the gate poses kept changing, and if they did not change after the second episode, then we would tune our controller and assume that the poses were known because we had learned them in previous episodes. But we discarded at the very last moment because we realized that it will score very badly on the second part of the scoring with the episode, just because of the extra flight time and the extra episodes that we will require. So instead of that, we opted for a larger lap time on like a single episode, instead of having configuration that in average reduce the time in about 1.5 seconds for the same safety level that our current solution has. So that's something that we noticed.
Yeah, thank you for raising. Yes, yes, I agree. It is a difficult question to assess what's fair in terms of how much simulation time is unfair for a learning-based system to actually use. So, like, why should we penalize someone who wants to learn a lot more in simulation? Yeah, I'll definitely keep that in mind. Thanks. I think we can wrap this up. Thank you so much for all the work. I'll be in contact with the prizes, with the exit survey to essentially everyone who ever registered for the competition, and possibly to write a paper together. That would be nice.
Awesome, thank you.
Thank you for all the effort you put into this competition. It was really fun, as I said before. We learned a lot from it, so thank you for it.
No, it's awesome to hear that.
Thanks for hosting the competition, Jacopo, and for coordinating and writing back and forth with us.
My pleasure. Okay. Have a good afternoon, night, morning, wherever. Bye-bye.